The step, firstly, we calculate the mean and the variance using the formula provided in MF19. The second step, you need to remember the method of the continuity correction. In this case, greater than 40, we add 0.5 to exclude the 40. Third step, calculate the z-score. The fourth step, use the MF19 table to calculate the area on the left. And if the question asks you for the area probability greater than something, area on the right, then take 100% and minus the area on the left, and you get the final answer. Huh? Thank you very much for spending time watching this video. If you have any question, please leave a comment in the comment box. Thank you, and I hope to see you again. Hello, and welcome to IB and A-Level Learning Center with Nita Thai. In this video, I would like to introduce to you the reason why we need to do the normal approximation in A-Level Statistics, paper 5, and the condition and the method, including specific steps within specific example, detailed example about how to apply the normal approximation to the binomial distribution. Even want to do this, why would we do it? Now, why would we even want to do this? Well, when the number of trials become very large, calculating the exact binomial probabilities becomes very time-consuming. So instead, we use a smooth normal curve to estimate those probabilities much faster. As the number of trials increases, the shape of the binomial distribution begins to look more and more like a bell-shaped curve, and that is exactly why the normal approximate works. Let me show you with simulation. We have these columns represent the probability of a binomial distribution with the number of trials 17. I can change it like 20, and the probability 50%. Yeah, 0.5, 50%. Okay. The height of each column represents the probability that we get a value exactly to a number. For example, the probability that we get the exact value A, such as 8 minutes for a runner to complete a race, is 0.12, approximately 0.12, something like that. And the binomial distribution only deal with integers 1, 2, 3, 4, 5. It cannot solve the problem with continuous variables. Real number, it cannot calculate the probability of a value, real value such as 1.2. So when I click on this normal curve, I see that the curve here is called the bell curve. It represents the normal distribution. And sometimes with 3 conditions, the normal distribution can be used for an approximation of the binomial distribution. So I want to move the bell curve so that it is almost fixed the distribution of the rectangular columns. So I will change the mean here. It is now the mean of the normal distribution is 9. Let me increase that to 10 here, so that the peak value of the curve and the middle, it is also the middle, the mean of the normal distribution is now 10. And I will change the standard deviation here also, so that the curve fit the best with the columns, rectangular columns. You can see if it's good now, huh? So this is a very good approximation that the probability that we get some values such as, okay, here I can move the region, huh? For the binomial distribution here, I have the probability of getting values from 5 to 6, including both value 5 and 6, lower bound, upper bound. This probability is 0.052. I will choose the normal distribution here, 5, huh? So I choose the continuity correction here, like 4.5 here. And then to 6, choose 6.5 here. Okay, so now I have the probability of a normal distribution, so that the value is covered is from 4.5 to 6.5 is 0.056, which is very close to 0.052. I'll explain later in several minutes about the continuity correction, the reason why we need to do this correction, taking the value x 0.5 units smaller than 5 and 0.5 unit greater than 6 later. Okay, the point I'm representing right now is the condition that we can do an approximation. Okay, one more time, the normal approximation is used when the number of trials is extremely large or very large. So it is hard to calculate the binomial probability using manual formula rather than using a computer, of course. And now we have 3 conditions to use normal distribution for the binomial distribution. The first thing, the sample size n is very large. It's not necessarily like 100, 200, 1,000. It can be like 10 or 20 something, but large enough. This is just one first condition, which is like the necessary condition, but not yet enough. We need 2 more conditions, okay? And all the conditions occurring at the same time is enough for using the approximation. The second condition, the probability of the binomial distribution is not too close to 0 or 1. And the best case is the probability of success in the binomial distribution is 0.5. Because the normal distribution is symmetrical, we have a bell curve. So when the probability of the binomial distribution is 0.5, the distribution of these columns is also symmetrical. If the probability is smaller than 0.5, like this one, it is right skewed. And when it is greater than 0.5 and closer to 1, it's called left skewed. The column, as you can see here, it gets higher and higher on the right hand, and it's very low on the left hand. That's why it's called left skewed. So when the 2 probabilities are far different from 0.5, 50%, the binomial is different from the normal approximation. And again, the best case is when the probability is 50% to ensure the symmetry of the binomial distribution. Okay, that is the second condition. And the third condition, which is critical, is that here we have these 2 things: the product of n and p, and here is the sample size of the binomial distribution, sample size, and multiply with p is the probability of success in the binomial distribution. The product here, n times p, is the mean of the normal distribution that we use for the approximation. Okay, and the second condition is that n times 1 minus p. 1 minus p is the probability of failure, which is 100% minus the probability of success, and times n greater than 5. These 2 conditions are satisfied. It is the third condition that we use the normal approximation. Okay. In this MF19, you have the formula for the approximation as well. Here it is. For the binomial distribution, the mean of our normal approximation is n times p. One more time, n is the sample size and p is the probability of success, and this thing is the variance. The next thing, which is very important and the most difficult thing for students, is the continuity correction. Most students lose marks here because it is kind of difficult for them to remember the rule of the continuity correction, because the binomial distribution deal with integer value 1, 2, 3, 4, okay, and the normal distribution deal with and this is the table that you need to understand the rule of the correction. For example, the probability of x equal a in the binomial, a specific value a, okay. For the normal distribution, we need to subtract 0.5 on the lower bound and add 0.5 on the upper bound. Why? Let's look at the diagram here. For example, we want to calculate the probability of getting the value 9 here, and you can see that the column, the height of this column is about 0.15. Okay, so for the normal distribution, I need to cover that column. If I put the value x is 9 here, this is 8.5 to 9.5, so that the boundaries of the normal distribution is the two edges, left edge and right edge of the column. Okay, so we can see that the probability calculated from the normal distribution is about 0.157, which is close to my approximation when I look at the graph here. Okay, so the exact value, we subtract 0.5 on the lower bound and add 0.5 on upper bound. Okay, greater than a, the property of the value x greater than a, we add 0.5 so that the normal distribution does not involve the value a. It excludes the value a. Okay. The next row, when we want to calculate the probability of x greater than at least a, in which the value a is involved, we will subtract the value a by 0.5, the correction, so that the lower bound is smaller than a, which means the value a is involved in the calculation. Okay. Oppositely, when x is smaller than a, we subtract 0.5, so that a is not involved. And finally, when a is involved and x smaller than at most a, equal to a involved, we add 0.5. You need to practice with several questions. Okay, I highly recommend the past paper question so that you remember the rule of the continuity correction. Why 0.5? In a discrete distribution, each integer represents an interval. For example, the integer from 10 to 11 the represent interval roughly from, okay, just move on. Now let's consider this example, which is a question from past paper, paper 52 in October 2023, paper 52, question number 3. Okay, a factory produces a certain type of electrical component. It is known that 50% of the components produced are faulty. A random sample of 200 components is chosen. Use an approximation to find the probability that more than 40 of these components are faulty. Okay, firstly, we can see that the sample size is 200, n here, sample size, okay? And the 15% is the probability of success. And success, in this case, is defined as the faulty product. Success doesn't mean something positive. It's some question. It means a bad thing. In this case, a faulty product. Okay. So, which question asks us specifically to calculate the probability that more than 40 components are faulty using the approximation. They specifically ask this approximation. So it means we should not use the binomial distribution to do the calculation, directly. One more thing is the number 40 sample size is pretty large, and therefore when you use the formula in the MF19 for the probabilities, you need to add the probabilities from 0 to 40, which are 40 values, which is extremely difficult to calculate all the terms and add 40 values together, of course, with no calculator allowed, for the automation, the full automation. Okay, so to do the normal approximation, we follow this step. Step 1, calculate the mean and standard deviation. Okay, the mean is sample size n multiplied with the probability. The n is 200 and the probability is 0.15. The mean is 30. Okay. Secondly, the variance, the sigma square variance is np times 1 minus p, which is the mean 30 multiplied with 1 minus 0.15, 85%. Okay. The variance 30 times 0.85, 25.5, 25.5 is the variance. Therefore, the standard deviation sigma is the square root of 25.5. Okay, now we can move on to step 2. Step 2, we need to do the continuity correction. We need to calculate the probability that there are greater than 40 components. Okay, more than, greater than, which means the value 40 is not involved. Therefore, the correction is that we would take the value 40 and add 0.5. Greater than, add it so that we exclude the 40 from the calculation. The next step, step 3, calculate the z-score. The z-score of the normal distribution for this value 40.5. One more time, we take the correction 40.5, not the original value 40. Okay, minus the mean 30 and divided by the standard deviation, which is the square root of 25.5. Okay, to calculate the z-score, 40.5 minus 30, the mean, put a bracket around it, and then divide the difference by the square root 25.5, which is the variance, and then square root is the standard deviation. We have 2.0793. I round it a little bit up by 2.08. Okay, I can take 79. 2.079 is okay. Okay, now I've got the z-score. The step 4, we just need to use the table, MF19 table, to calculate. Okay, let me illustrate that with the bell curve. This is the bell curve. This is the bell curve of the normal approximation, and the mean that we calculated, we got is 30. Okay, the standard deviation is something greater than 5, so like 35 here, one standard deviation. But the mean here 30 is standardized using the z-score formula. So the mean from 30 it becomes 0 here, and the standard deviation, of course, is 1 for the standardized distribution, normal distribution. Okay, we need a value z-score to be greater than. We need to calculate the probability. Okay, let me write it here. The probability that we need to calculate greater than 40 components is approximately the normal CDF with the lower bound 2.08. The upper bound is infinity. The mean is 30. Sorry, 2.05, 08 here is the standardized z value. So the mean is 0. One more time, the mean is 0, and the variance, the standard deviation is 1. The variance is also 1 for the standardized normal distribution. Okay, and the value 2.08 is something, because the standard deviation is 1. The value 1 is something like here. Here. The value 1 here. So the value 2 will be greater, much greater, and we have a tiny region here on the right, which is the answer is this tiny region. Okay. Now we use the MF19 formula. One very important thing in this table of the MF19 is that it only allows you to calculate the area on the left hand of the table of the normal curve. You can see the gray shaded region here, which is the probability getting a value x from negative infinity to a value z. For example, it's like 80% here in this diagram. Okay, it does not allow you to calculate the area on the right hand side directly. So this area on the right hand side is 100%, which means 1 minus the 80%. Okay, so we have the z-score 2.08. So I look at the table here to find that value 2.08. 2.0 is here. This one 2.0. Okay, and 0 and then 8. I will look at this value 0.8. This one. And the last thing, just 0.8, or we can take 7 and 9 here. But because it's extremely close to 2.08, so I would just use this column 2.08, and this is the probability 0.9812, which means the whole area on the left here is 98.2%. Okay, and the answer will be 1 minus 0.982. We check the value if I remember correctly. The value 9812. Okay, so now let's do that conclusion. The probability that I have a normal probability, a z value smaller than 0.28 from the formula MF19 is, formula table, MF19 is 0.9812, and therefore our answer, the probability that x greater than 40, approximately equal to the probability that the z value greater than 0.28 is 100%, 1 minus 0.9812, and the answer is 0.0 do that thing 0.188 0.0188. Okay, let me check the mark scheme. Here it is, question number 2, 3 something. Method 1, normal. Question 3. Okay, the normal approximation. You can see the correction 40.5 here, and the final result in the mark scheme 0.0188. Okay, so one more time, these are the steps to calculate the normal approximation for a binomial distribution with correct sample size, which is 40, with the two conditions. Let me remind you again, NP sample size greater than at least 5, and the second condition, n times 1 minus p, which is q, probability of failure, is also at least 5. Okay. The step, firstly, we calculate the mean and the variance using the formula provided in MF19. The second step, you need to remember the method of the continuity correction. In this case, greater than 40, we add 0.5 to exclude the 40. Third step, calculate the z-score. The fourth step, use the MF19 table to calculate the area on the left. And if the question asks you for the area probability greater than something, area on the right, then take 100% and minus the area on the left, and you get the final answer. Thank you very much for spending time watching this video. If you have any question, please leave a comment in the comment box. Thank you, and I hope to see you again.